Welcome to the podcast of the IEEE Transactions on Haptics. This podcast is designed to help you keep informed on topics in haptics while you're on the go by providing a brief summary of the articles in each issue. It is produced by Vincent Levesque, Ilana Niski, Mikhail Vyacheslevsky, and William Provancher, with the help of the authors of each article. This podcast gives an overview of the 14 articles found in the 2013 October through December issue.
This first article is a meta-analysis of the effectiveness of providing haptic feedback for improving task performance in virtual and real teleoperation. Its title is A Meta-Analysis of the Effects of Haptic Interfaces on Task Performance with Teleoperation Systems by Nitsch and Ferber. The goal of this research is to consolidate findings from the literature on effect sizes and heterogeneity in empirical investigations of the utility of different kinds of haptic feedback in improving teleoperated task performance. The paper presents a meta-analysis of empirical research results from 32 published papers about the effect of haptic feedback on task completion time, force regulation, and handling errors. The authors separately explored real versus virtual teleoperation and vibrotactile versus kinesthetic force feedback. They found that haptic feedback is very effective in improving task performance, and that the effect is less pronounced but more consistent in actual as opposed to virtual teleoperation tasks. Force feedback had larger effect on overall performance than vibrotactile feedback, especially in reducing error rate and improving force regulation. The significance of the work is in providing an empirical answer to the long-debated question of the utility of haptic feedback for task performance. This next article explores how the direction of an applied force influences the perception of its direction and magnitude. Its title is Anisotropy in the Haptic Perception of Force Direction and Magnitude by Van Beek et al. The goal of this research is to investigate human perception of the direction and magnitude of horizontal forces applied to an extended hand. This paper presents a psychophysical study in which participants were asked to indicate the perceived direction and magnitude of horizontal forces that were applied on their hand. The magnitudes of the forces ranged between 2 and 6 newtons, and applied directions covered 3/4 of the horizontal plane. The authors found that haptic perception of force magnitude and direction is anisotropic in the horizontal plane. This means that humans perceive the same force differently when it is exerted on their hand in a different direction. The distortion of force magnitude had a consistent elliptical pattern in which the forces that were in line with the arm of the user were perceived as being smaller. These findings advance the fundamental understanding of the psychophysics of force perception and are important for the design of haptic interfaces.
This next article investigates the contribution of different haptic cues on curvature perception with a novel haptic device. Its title is Contribution of Slip Cue to Curvature Perception through Active and Dynamic Touch by Zhang et al. The goal of this research is to develop and evaluate a haptic display that accurately replicates the cues used for curvature perception, and more specifically to study the contribution of the slip cue. The authors designed a haptic display that independently controls the orientation, elevation, and translation of a flat plate, and motion algorithms that reproduce curvature cues such as position, local slope, and slip. The authors conducted 3 experiments to determine whether the device can render curvature through active touch, and more specifically to investigate the role of the slip cue in the perception of curvature. The authors conclude that the slip cue makes a significant contribution to curvature perception and that their haptic device accurately simulates curvature. The main contributions of this paper are the design of a novel haptic device for curvature display and a new result on the role of slip in curvature perception. This next article proposes advances in the haptic rendering of deformable objects for distributed virtual environments. Its title is Distributed Haptic Interactions with Physically Based 3D Deformable Models over Lossy Networks by Tang et al. The goal of this research is to enable the simulation of haptic interactions in virtual environments distributed over communication networks with packet loss, delay, and jitter. The authors propose a novel approach to support distributed haptic interactions with physically based 3D deformable models. The approach achieves a very small network load and low computational costs, and is robust to common communication issues in client-server and peer-to-peer networks. The authors report a theoretical analysis of the approach's performance and experimental results with simulated network conditions. The authors conclude that the proposed approach is valid, effective, and robust. The main contribution of this paper is the design and validation of a novel approach to providing haptic interactions distributed on a network in virtual environments.
This next article develops a method for estimating the interaction force between a parallel haptic device and the hand of the user. Its title is Dynamics Modeling for Parallel Haptic Interfaces with Force Sensing and Control by Bernstein et al. The goal of the research was to generate a new model for estimation of a user-device interaction force based on measurements from 5 one-dimensional force sensors that are mounted on the actuator rods of 5 degrees of freedom parallel haptic device. The paper presents an analytical derivation of the relationship between the forces that are measured at each one-dimensional force sensor and the interaction force. Then, the authors derived the added modeling terms for the haptic device to create an accurate estimation of the interaction force. These terms may be calculated analytically or identified by attaching external force sensors to the haptic device. The authors found that when lateral mechanism impedance of a parallel haptic device is small, interaction force may be estimated directly from the sensed forces. For the other cases, they developed a new augmented model for accurate force estimation. The significance of this work is in revealing the implications of using one-dimensional force sensors in the construction of new haptic interfaces on the ability to accurately control interaction force, and in demonstrating an analytical solution for overcoming these inaccuracies for a 5 degree of freedom parallel haptic interface. This next article investigated haptic assistance policies in human-machine collaborative tasks. Its title is Exploring the Design Space of Haptic Assistance, the Assistance Policy Module, by Passenberg et al. The goal of this research is to explore the influence of the strength of haptic assistance, its adaptation to user performance, and the choice of performance criteria on the quality of human-machine collaboration. The authors have introduced a novel module that determines the level of machine haptic assistance based on 3 components: performance criteria, performance reference, and assistance policy. They evaluated several implementations of the components in a multiple users study using a maze with obstacles task. The authors found that adapting the level of assistance is better than using a constant level, and that an adaptation policy of switching between 2 discrete levels of assistance is better than continuous adjustment. They also found that performance measures that are based on multiple criteria lead to a favorable performance over a single optimization criterion, and that the selection of the reference path for controlling the haptic assistance depends on the application. The main contribution of this work is a systematic mapping of the trade-offs in determining the level and policy of haptic assistance that may be used for various applications such as rehabilitation, mobility aids, and driver assistance systems.
This next article investigates the limits of human perception to determine the minimal performance requirements for a haptic feedback system. Its title is Human Detection and Discrimination of Tactile Repeatability, Mechanical Backlash, and Temporal Delay in a Combined Tactile Kinesthetic Haptic Display System by Toxin et al. The goal of this research is to better understand the limits of human perception in order to design smaller, less expensive, and more useful tactile kinesthetic displays. The authors conducted 3 experiments to evaluate the perceptual limits for sensitivity to tactile positioning, system backlash, and system delay of a haptic system with contact location feedback and kinesthetic feedback. Tactile positioning was evaluated with a position matching task, while backlash and delays were evaluated by observing the effect of artificially decreasing performance. The authors found perceptual limits for positioning, backlash, and delay that will enable the design of simpler devices without compromising the quality of haptic simulations. The main contributions of this paper are new results on the limits of human perception that provide useful constraints for the design of tactile kinesthetic devices.
This next article proposes a novel classifier for human haptic exploration procedures for 2-dimensional raised surfaces. Its title is Identifying Haptic Exploratory Procedures by Analyzing Hand Dynamics and Contact Force by Janssen et al. The goal of this research is to build an automatic classifier of haptic exploratory procedures, where exploratory procedures are the typical hand movements that are used for acquisition of specific object properties. The authors first investigated hand movements and contact forces of users during performance of 5 exploratory procedures and identified important features for classification. Then, they constructed a model for each of the procedures based on the value of the identified features and build a classifier based on the least squares distance from the model. Finally, they tested the classifier in trials under free exploration. The main contribution of this work is a novel method for automatic exploratory procedure classification that is based on hand movements and contact forces. The developed classifier exceeds 95% accuracy when applied to the closed set of 5 exploratory procedures that were examined in this study. However, its consistency is reduced in unstructured exploration. An automatic classifier could be a useful tool in the study of haptic exploration and for identifying a user's intention in haptic interaction.
This next article studies the human's ability to create mental maps from haptic exploration of virtual objects. It's entitled Predicting Successful Tactile Mapping of Virtual Objects by Breda et al. This paper presents a study that uses a minimalistic tactile device called the tactile mouse to render height maps. The device is used to compare the ability to create tactile maps from a simple feedback of both visually impaired and sight participants. The author established a mathematical model that evaluates the quality of construction of mental map from touch. The model is able to evaluate, predict, and track spatial abilities of blind and visually impaired subjects. The work provides a new look at the mental processes responsible for the construction of mental maps from tactile inputs, as well as our abilities to orient in new spaces.
This next article studies the effectiveness of various control strategies for the teleoperation of mobile robots with articulated arms. Its title is Task Performance Evaluation of Asymmetric Semi-Autonomous Teleoperation of Mobile Twin-Arm Robotic Manipulators by Malish et al. The goal of this research is to establish guidelines for developing effective control strategies for complex, high degree of freedom teleoperation systems, and more specifically for mobile manipulators with articulated arms. The authors conducted a series of human factor experiments involving maneuvering and grasping tasks. Simplified configurations are first examined to explore control methods for different aspects of teleoperation. This is followed by dual arm and dual operator teleoperation maneuverability experiments, as well as a comprehensive experiment on the dual operator teleoperation of a custom-built twin-arm mobile manipulator. This paper demonstrates that specific control strategies and system configurations can enhance navigation, grasping, and multi-user cooperation in the teleoperation of high degree of freedom systems such as mobile twin-arm robots. The main contributions of this paper are new results on the effectiveness of different control strategies for teleoperation.
This next article investigates the physical parameters that play a role in the perception of roughness during the exploration of a textured surface with a tool. And it's entitled The Physical Basis of Perceived Roughness in Virtual Sinusoidal Textures by Unger, Klatsky, and Hollis. The goal of this research is to understand the connection between what people feel as they run a tool over a surface and how rough the surface seems to them. This paper presents a psychophysical study in which participants were asked to judge roughness of surface texture that are simulated by a force rendering device. Their judgment, along with physical measurements as they explore the surface, were used to identify exactly just what they are sensing that leads them to perceive the surface roughness. The authors found that the computed spectral power of the force signal is strongly correlated with the perceived roughness of sinusoidal texture. These results are important because they indicate what is needed to convey the sense of roughness in virtual environments. They will inform developers as to what is needed to make texture feel rough, regardless of the device that is used. This next article presents the design and evaluation of a novel, wearable haptic device that provides cutaneous force feedback to the user's fingertips. Its title is Towards Wearability in Fingertip Haptics, a 3 degrees of freedom wearable device for cutaneous force feedback, by Pratikitso and colleagues. The goal of this research is the development of a 3 degrees of freedom wearable haptic interface that can provide contact forces at the fingertips. This paper presents the design of the device along with the psychophysical validation. The device consists in 2 halves, one portion that contains actuators and is placed on the back of the finger, and a second portion composed of a moving plate in contact with the finger pad. Tendons transmit forces from the actuators to the plate. The structure of the device resembles that of parallel robots, where the fingertips is placed in between the static and the moving platforms. A curvature discrimination experiment is used to evaluate the effectiveness of the device. The authors found that employing their device together with a popular haptic interface improved the curvature discrimination performance. They provide guidelines for the design and evaluation of such wearable tactile interface. These devices are of interest of researchers who deal with teleoperation and haptic rendering, since they can provide tactile cues when kinesthetic force feedback will affect the safety of the system.
This next article investigates the emotional and subjective characteristics associated with haptic illusions of movement on the skin created by different forms of vibrotactile feedback. Its title is Comparison of Saltation, Amplitude Modulation, and a Hybrid Method of Vibrotactile Stimulation by Raizamo, and Suraka. The goal of this research is to compare the emotional and subjective characteristics of 3 methods to elicit illusory movement on the skin with vibrotactile feedback. The authors conducted a perceptual study in which participants were asked to rate the continuity, pleasantness, and arousal of illusory motion produced on the forearm with 3 vibrotactile actuators. The motion illusion was produced using either saltation, amplitude modulation, or a hybrid method. The authors found that amplitude modulation resulted in a more continuous, more pleasant, and less arousing illusion. They also found that continuity is strongly correlated to pleasantness and arousal. The main contributions of this paper are new results on the link between haptics and human emotions.
This last article presents the perceptual analysis of a moving sensation called vibrotactile flow that is created using vibrating actuators. The article title is Perceptual Analysis of Vibrotactile Flows on a Mobile Device by So and Choi. The goal of this research is to find a perceptual framework for vibrotactile flow that maps the vibrotactile signals with desired perceptual properties, such as intensity, distance, velocity, and the strength of the flow sensation. This paper presents a perceptual analysis that ties the vibration signal characteristics to human perception of vibrotactile flow. Vibrotactile flow sensation is created by modulating the amplitude of a signal sent to multiple actuators, distributed onto the skin. Increasing the stimulation on one side while decreasing on the other gives the sensation of a moving object. The experiment tied the perception of a moving sensation to multiple characteristics of the vibration signal. This information is then reversed to synthesize calibrated vibrotactile signals. The authors found a set of mathematical functions that describe the perceptual characteristics of vibrotactile flow. This knowledge contributes to the development of applications that use vibrotactile flow and can enrich the interaction on mobile devices.
This concludes our podcast for this issue of the IEEE Transactions on Haptics. Hope you'll tune in again for our next issue.